So thank you to you and to Chris and to everyone who's helped with the organisation. And may I just say, particularly as an Englishman, how much it means to be invited here to Boston. It just shows that even after all these years that there really are no hard feelings. Okay, so I'm going to talk about two different experiments we've been doing in Oxford, and single-qubit operations in calcium-43 hyperfine clock qubits with microwave-driven single-qubit gates in this surface trap here. And then, secondly, some more recent work we've been doing on two-qubit gates, also in calcium-43 hyperfine qubits, but not the clock qubit, and driven by lasers here instead of microwaves. And this is in a more conventional macroscopic Innsbruck-style blade trap. Okay, so I entitled my talk High-Fidelity, and I guess I should say something about how high is high. What does this mean in the context of quantum information processing? So obviously, the science of quantum error correction is a highly technical field, and I can't hope to really say very definite things about this. But if I go back to some older work, for example, of my colleague Andrew Steen at Oxford from 2003 as a paper on overhead noise threshold of fault-tolerant error correction, where he's really looking at the issues of what happens for a given gate error. As we all know, there is an overhead in terms of both the physical resources you need and the number of operations you need to do. Here, this is I think as Eric Hudson said, that log-log plots hide a multitude of sins. This is a log-log-log plot. And you can play the devil yourself. Here is the gate error, log of the gate error. This is the scale up, which I believe here is just the ratio of physical qubits to logical qubits. And this is the log of the number of operations your quantum computer can do before it falls over. If you look, for example, at a gate error of 10 to the minus 3, and you look along there, well, yeah, you can get something that's going to work, but the scale-up factor is getting pretty scary and huge over there. Obviously, it's much better to push into this regime where you can get your errors as small as possible, and then maybe you can even work a scale-up of somewhere between 10 and 100 and do, 10 to the 10 operations, 10 billion operations. That would be good enough for me. Obviously, I guess the message is simply that the lower you can make your error rates, the better, and that there is a severe penalty to be paid. And I think that, obviously, error correction science, I'm sure, has moved on since then, but I think that's, as a general point, is still true. Here's a more recent piece of work from Fowler, published last year in PRL. And so what he says here is he's looking at surface code error correction. And he's saying we take all the single-qubit operations and two-qubit gates with a certain error rate, and we prove that arbitrarily reliable quantum computation is possible provided p is less than 7 × 10⁻⁷, a target that many experiments have already achieved. Well, that's news to me. I haven't seen a two-qubit gate at those kind of levels. Apparently this proves the experimental feasibility of quantum computation, which to an experimentalist, I don't know how you prove the experimental feasibility of something apart from doing it in the lab. Anyway, so we work with calcium-43, and again, this is something of a long history at Oxford. Again, if you go back to one of Andrew's early papers, as a nice introductory paper on ion trap quantum information processor dating back to 1996, he discusses choice of various ions, and he actually zeroes in on calcium-43 and has a level diagram of it here. And there's a comment in the paper: the choice of RF rather than optical transitions for information processing appears so advantageous as to be forced upon us. So, even back then, obviously, the idea of using microwave or RF sources to drive your qubit transitions in some way was clearly very advantageous. Now, notwithstanding that, of course, Innsbruck have done a whole host of wonderful experiments using the optical qubit on that 729 nanometer transition, of course, and justly famous for doing so. But there's clearly an attraction to be had in having your qubits down here in the ground hyperfine states, as has been demonstrated again by an equally marvellous series of experiments from Boulder. So calcium-43, this is a 3.2 gigahertz microwave transition, and here again on that diagram is also indicated the basic Raman laser manipulation using the 397 nanometer transition of the qubit, which allows you to couple to the motion and do multi-qubit gates. We first actually worked with calcium-43 in the lab several years later than that. That was one of our first laser-cooled crystals of calcium-43. I think we were maybe the first people to laser-cool calcium-43. Not the first people to trap it, Gunther had already done that. We also measured a coherence time using the magnetic field independent m equals 0 to 0 transition down here of about 1 second. That was done by Ben Keach a few years later. And of course, I shouldn't forget that Innsbruck as well did some very nice experiments on calcium-43, including some high-fidelity two-qubit gates. Around 2007, 2009, Jan Benhelm and Christian Roos were the main people doing that. Okay, so let me come then on to the first real part of my talk, single-qubit operations. And I'm sure several of you would have heard most of these results already, so I'll try and whip through fairly quickly. But here's our qubit, zooming in on the ground state of calcium-43, and as you increase the static magnetic field, you get Zeeman splittings and some curvature, which isn't very evident there, but that particular transition, because 0 to +1 at 146 Gauss, becomes field independent. That is, there's a turning point in the transition frequency there, and that obviously makes it stable to magnetic field fluctuations, which are our leading source of noise in the lab. So later on in the talk, I'll also be talking about work, right? Talk about the laser-driven two-qubit gates. They're going to be on this so-called stretch qubit using the stretch states at the end of the manifold there. At 146 Gauss, we have about a 50 megahertz Zeeman splitting, and this is also nice because you can drive these microwave transitions relatively fast. So, for example, when we're preparing the qubit here, we optically pump down to this 4+4 stretch state, and then do a series of 3 microwave pi pulses, and we do those take about a microsecond each. And that's nice because these transitions, these green ones, of course, still are magnetic field dependent, and so we still have to beat the noise there if we want to be able to get in and out of the qubit states with high fidelity. These intermediate field qubits were first demonstrated at NIST, have been used in beryllium and magnesium. Calcium has, both an advantage and disadvantage. It has these low-lying D states, of course, which complicates things like laser cooling. But it does allow you to use the shelving technique for readout, which is a slight gain, and the visible transitions are possibly attractive, particularly for the microfabricated surface traps. We don't see charging problems, and maybe there's more possibility of using integrated optics in the future vision. And the laser systems are all diodes. The blue transitions come from direct diode lasers. Now, of course, it's not just the ground state that gets split by the magnetic field, it's also P-half and D3-half, so there's quite a messy level system at 146 Gauss. So the first challenge was to Doppler cool this, and it wasn't obvious we could do it when we started this project, but work by Derek Stacy and Hugo Janaszek on simulating the system with block equations and searching around for good solutions. Zeroed on a nice simple solution, which is really no more complicated than laser cooling calcium-43 at low magnetic field. That is, you have your blue laser, and you have one EOM sideband on it, and one single frequency for the red repumping laser at 866 nanometers. That's all you need, and you can get decent amounts of fluorescence off the ion. This is a scan then of the repumping laser, showing there's a whole forest of dark resonance there, but we think we understand what's going on because the numerical model fits quite well. So we get typical fluorescence rates, which are similar. So the only big difference really is that you need a relatively high intensity of the 397 nanometer laser, and again, in the microfabricated traps, or when you're close to the surface, that could be an issue. So we get as much as 10% background there. That's where that's an issue is when you're trying to do the readout. So this is a plot of how well you can do the fluorescence detection and readout. So these are the error contours as a function of basically the ion fluorescence rate and the signal's background rate. So calcium-40 is somewhere up here, and we can get to 10 to the -4 level for fluorescence state readout. Calcium-43, the signal to background is about a factor of 10 worse. This is another log plot, isn't it? And that makes the readout maybe a factor of 2 worse, but not too bad. Right? This contour is pretty much vertical on that plot. So how do we do that readout? Once we're in the qubit states, we take this qubit state, first take this qubit state over here, so the 1 state ends up here, and then we take the 0 state up there, so they're in states which are split by around about 3 gigahertz. and then we apply this optical pumping shelving protocol to transfer that state over to the D5 shelf while leaving that state down there. And so this is the cycling transition that one would use in beryllium or magnesium. And this repumping over here with these 850 nanometer polarizations sort of plugs the hole, which is decay to the D3 half state, and keeps this a sort of closed transition. And in fact, basically that repumping over there is basically perfect. So you can forget about that. And then what you've got is just the cycling transition as in beryllium or magnesium. What limits the fidelity is exactly the same thing. It's the off-resonant excitation of the other qubit states, which is about 3 gigahertz away. And compare with your the chance of getting into the shelf. And there's really a very direct comparison here. The branching ratio here is about 5%. So if you want to be in that shelf with greater than, say, 99.99% probability, you want to make sure your qubit has not, the probability of being left down here is 10 to the minus 4. So that means you need to scatter about 8 of those photons. Okay? Then e to the minus 8 is the probability that they will be down there, and e squared in experimentalist units is 10, right? So that's about a 10 to the minus 4 error. If you're using beryllium, this is not the D5 half shelf anymore, this is your PMT. And the 5% branching ratio is not the 5% branching ratio, but it's the collection efficiency of your optics. It's exactly the same problem. The chance of, again, you want to scatter about 8 photons. The chance of you getting 0 photons on your beryllium cycling transition is then e to the minus 8, just from the Poisson distribution. So it's the same thing. So the reason you get a gain here is you've got a 5% branching ratio, and typical detection efficiencies are about 0.1, 0.2%. Unless your name is Young-Sang Kim, who has about 2.5% detection efficiency, and therefore is getting close to this situation. Once you've got it in the shelf, you do the fluorescence detection. We do use this time-resolved method we first did a few years ago, where we collect the photons and actually just time tag them. This gives you a little bit more information. You can squeeze out, gives about a factor of 2 improvement in the fluorescence detection. These are histograms. Now, you're used to seeing photon count histograms. These aren't photon counts. What you do when you get this time-resolved record here is you work out the likelihood of the ion being bright or dark. So this along here, it's the log likelihood ratio. Okay, so 0 here is where that likelihood is more likely that it's bright or dark. And this is just preparing the ion in the dark state. This is preparing the bright state. And this, where those histograms overlap, as usual, is the error down there. And in this example, it's about 2 10 to the minus 4. So in the clock state, we do this. We do the preparation, and the preparation and readout, we measure a net error of about 7 10 to the minus 4. We can't separate those out. This is where we think the errors are coming from a few different control experiments. We think that the preparation, actually, the stretch state is really good, better than 10 to the minus 4. The microwave pulses in and out of the qubit add up to about 4 10 to the minus 4. There's about 7 pulses there. The shelving protocol, optical pumping to shelf, is about 1/2 10 to the minus 4. The fluorescence detection about the same. And all those errors, except that shelving one, are all just technically limited. You could make all the others better. You can make the fluorescence detection better by having a bigger lens. This one is limited by the atomic structure at about the 1 10 to the minus 4 level. And so the optical techniques here, we've got commercial diode lasers, we've got low power levels, no frequency doubling, and so on. So I think that, relevant to the scalability, which will be topic of discussion next week, that's an advantage here. Okay, so coming back to the clock qubit, once we can prepare and read it out, we do the microspectroscopy as a function of the magnetic field here. Here's the clock transition frequency around 3 gigahertz. And here's this field independent point. The curvature is about 1.2 kilohertz per Gauss squared. So therefore, with typical milligauss field fluctuations, if you're in the right place, you're looking at millihertz qubit fluctuations. We can find the right place. Obviously, that's tricky from here because you're at the minimum. But if you look at the stretch transition, this is the standard trick from atomic clocks, which is linearly dependent. Then you can set to the right frequency using the right Rabi formula for the known ground state hyperfine structure. If we zoom right in on the center there, we can really see that minimum to a sort of Hertz level precision or better. And this 0 here, I should say, we observe about an 8 Hertz shift from the oscillating RF currents in the trap electrodes, which is a known issue of these traps, but again, provided that's stable, will stay in the right place. So we measure the coherence time using Ramsey microwave spectroscopy of the qubits with delays up to 16 seconds. This is Ramsey fringe contrast. It's obviously long and painful experiments. Out of that comes a T2 coherence time of about 48 seconds. This is obviously much better than the 1 second we measured in the low field independent qubit, clock qubits. It's a little bit better than the 15 seconds in the comparable Brilliant intermediate field qubit, but still nowhere near the John Bollinger's amazing 10 minutes record in the high field clock states. And the reason, I guess one of the reasons there is these high field clock states which go over the fields of order of Tesla. Again, there's turning points there, and the curvature there is several orders of magnitude smaller, so you can win big over there. But I think for our purposes, 50 seconds is more than enough. For fun, we also did this with a CPMG sequence with about 500 dynamic decoupling pulses inside the Ramsey gap, and we observe that much contrast at 16 seconds. And in fact, this is probably telling us that there's systematic stuff going on here as well, that after 16 seconds in the dark, the ion is heating up, the readout is not working as well, and it's probably that rather than kind of real decoherence, which is the issue. We also did randomized benchmarking on this clock qubit driven by microwaves directly from the trap electrodes in this surface trap, and we just followed the recipe from Manny Mill and others about applying a series of random pi/2 pulses interspersed with pi pulses around random axes in the Box sphere, rotating into the measurement basis of measuring. And here's a set of data from here. So this is the number of computational gates, each of which on average is about 2 physical gates, pi/2 rotations. And this is the total error added up. So there's a baseline here from our readout error. That's the same level we independently measured in the readout experiment. It's about 7 × 10⁻⁴. And the gradient there indicates that the error per gate here is about 1 part per million, which is very satisfactory. That's with a 12 microsecond pi/2 time. We also went a bit faster, 4 microsecond pi/2 time. We've got an error per gate of about 3 ppm. And this is all with just a milliwatt or so of microwave power, because it's in a surface trap. You don't need to put much power into the trap. I'll talk a bit about the trap anon. So we also wanted to make sure we understood what's going on in this system. So we looked at we deliberately tried to make things worse. So here's our clock transition. We looked at the randomized benchmarking error as a function of setting the detuning incorrectly, which we can model then. So the curve is a model of what we expect to happen when we do this. And here's some data which broadly agrees with that. The other significant error here is in setting the microwave power, in other words, the pi/2 pulse area. And so again, if we induce deliberate errors here, that gives us close to what we expect to be the error here. Incidentally, in the experiment, we were continuously, from time to time, calibrating this area by putting in a long series of pi/2 pulses. And from the drifts in the calibrated power, we think that the actual fluctuations in that area are about 10 times smaller than this. So in the actual experiment, we're somewhere sitting in here, which is consistent with this sort of 1 part per million error. This is where we think the different errors are coming from. Here, there's a certain amount of detuning error because we weren't quite sitting in the center of the clock qubit. There's an AC Zeeman shift from spectator transitions, which comes in with a small area here. That's what we think the pulse area error. And there's also a little bit of leakage from off-resonant excitations to other states in the manifold. Okay, so I haven't said anything about the trap in which this is all done yet, but the trap is a surface trap incorporating integrated microwave electrodes, originally designed to try and implement this proposal, which was also done in Boulder a couple of years ago, of microwave-driven 2-qubit gates. Okay, so here using the microwave field gradient, the idea is that the microwave currents here, you can null the microwave field, and here's our experimental field map around here, measured by moving the ion around, and there's a gradient of the magnetic field here, and that can talk to the motion of the ions rather like the gradient of the laser field does in laser-driven gates, and there's some advantages here. You're less sensitive to the temperature of the ions and so on. And of course, in principle, you are then doing all your gates by electronic methods instead of laser methods. The big difficulty is the microwaves couple weakly to the motion of the ions. That's the experimental challenge. Here's the trap design. So this was very much David Alcock's brainchild. And the novel feature of this trap, I guess, is that it incorporates these microwave sort of circuit elements like coplanar waveguides and quarter wave couplers, and there's a half wave resonator here to increase the microwave current in the trap region to get a little bit of enhancement there. And the nice thing is it's all designed as a 50 ohm system from the outside world, and so we couple in something like 70% of the microwave power. Yeah, so we can do these single qubit gates with very low power levels. That's what it actually looks like. The trap performs very well. It has a heating rate, which on this sort of plot of all heating rates for a room temperature trap, which it is, compares very well. These are all cryogenic points, except this is the argon ion cleaned trap from NIST down here, so we haven't done any special cleaning or anything with this trap. It just worked really well. So we have done a little bit of motional control with the microwaves, mostly with single ion up to now. So that's what the gradient looks like, and we can see the microwave motional sidebands here. So here's this is a scan of the red and blue sideband, telling us something about the motional mode occupation number on the radial mode of the trap. This is with a 2 millisecond sideband pulse, so still a relatively low microwave power. And I'll just come back to something about the Doppler cooling here. So I showed earlier on a much wider frequency scan than this. This is the repumping laser, and this is the ion fluorescence. And there was this forest of dark resonances there. Now, most of those dark resonances are not very dark because there's so many different states in the cooling manifold that there'll be some light which will pump you out of the dark states. This one here is an interesting one because this involves the states right at the high M end of the manifolds here between S half, P half, D3 halves. So the dark state you get here when there's a Raman resonance between the red and the blue laser is of course superposition of S half and D3 half states. And with the polarizations we have, there's no way of pumping out of those states. So that particular dark resonance there is properly dark, or should be properly dark. And it's also a relatively narrow feature, so this is something like 20 megahertz across. So by sitting in there, we can cool more efficiently than if we're just sitting out here on this much broader fluorescence curve. So this is the estimated N-bar measured using the microwave sidebands as we scan or sit in different places on this dark resonance. You can see here we get down to, this is the calcium-40 standard Doppler limit here. So we can use this dark resonance, or over here, using another one over here, we also get down close to that temperature. And these are points for the two different radial modes in the trap. Let me go on to this. This is a little bit of work with sideband cooling of two ions here, where we're excuse me, we're seeing a bit of cooling of the radial mode here down to N-bar of about 0.3. And we also use the sideband thermometry using the sidebands to measure a heating rate on the radial mode here, which is about 0.1 quantum per millisecond at 2.8 megahertz. And that's roughly consistent with the heating rate we previously estimated just from the Doppler recall method. Excuse me. Okay, so much for single qubit stuff and microwave manipulation. I'll come on to talking about the two qubit gates in this other experiment. So this is the macroscopic trap. Here are the key parameters. The iron's about 0.5 millimeter away from the electrode. The axial heating rate, so I'm going to use the axial mode for doing the gates, is about 1 quanta per second. Measured motional coherence time of order 200 milliseconds. So it performs well, and as you'd expect for a reasonably large trap. So we're going to be wanting to drive Raman transitions, as I mentioned at the beginning, calcium-43 is the 3 gigahertz splitting. So here's a little bit of detail on the Raman laser system. So this is a pair of commercial frequency doubled tapered amplifier diode systems. So the only modifications we made here is that we have 2 of these systems, and one of them we call the master injects the other one, the slave, so injects the diode, and it can inject either directly if we want to work with calcium-40, or if we're working with calcium-43 via a 1.6 gigahertz shift with an AOM. So in the blue we end up with a 3.2 gigahertz shift to span the hyperfine structure. So frequency doubling, of course, always gives intensity noise. So there's various feedback loops to try and stabilize the intensity feedback to the tapered amplifier here. These are AOMs we use for switching the beams on and off. We have short fibers here to get better beam pointing stability, and then, of course, after the fibers introduce intensity drift as well, so we feed back to the AOMs to keep the power of those beams constant. And we're working with, we've chosen a very conservative large spot size of about 60 microns so we don't have too much beam position drift at the ions, and we have about 5 milliwatts available in each of these Raman beams. Okay, so one experiment we did here was to see how to really make sure this is spectrally pure, this laser. So what we do here is look at the scattering rate compared to the light shift. Scattering rate for a given intensity, essentially, but we're just using the light shift to measure the intensity of the ion. So we do this with calcium-40. If we prepare the ion here, then we put on the sigma plus beam. It's very far detuned from PR. We get a light shift here, which we measure to calibrate intensity. We're going to see how long it takes for the ion to get optically pumped to the other state to measure the scattering rate. So, so this scattering rate is going to be proportional roughly to the line width over the detuning here. This detuning is still quite small compared with the P1/2, P3 halves fine structure splitting in calcium, which is 7,000 gigahertz. Then it's not quite such a simple formula, but this agrees nicely, so the laser system looks definitely monochromatic. If we work at our standard detuning of about 450 gigahertz, for example, then when we do a carrier pi pulse with the laser, we get a 10 to the minus 4 error doing that. We do have intensity noise, as I mentioned. So this is the time scale on here in microseconds. This is the intensity noise, and this is magnified. There's only 2% here, peak to peak, but it's still something we'd rather not have. And this is with all these feedback loops and stabilization optimals. We haven't really got a very fast feedback system. I'm sure if we had put a bit of effort into an electro-optic feedback system, we could make this a lot better. At the moment, we don't think it's a limitation. We have done a bit of work exploring an alternative laser system using blue diodes instead of these frequency double systems, which I won't talk about, but I have some slides if anyone's interested. So we can look at the intensity stability on the long term at the ion. This is the Rabi frequency at the ion. It's a 10 to the minus 4 over several hours here. So we see a sort of long-term drift of about 2 10 to the minus 4 per hour. So this is measured with the ion. And the noise here is a combination of just statistical noise, measurement noise, but also there's the 10-minute cycling time of our lab air conditioning, which you definitely see in here. Obviously, we also care for the Raman transitions about the stability of the Raman difference frequency, which we put on using RF with the AOMs, but of course there's an interferometer there, and it's a reasonably big interferometer. So we take these two beams, beat them together on a fast photodiode at 3 gigahertz, and look at the beat note, and this is comfortably small, so that certainly shouldn't be an issue. So that's some stuff on the diode-based laser system, which I won't talk about now. So the gate we're implementing is the Didi-Leibfried gate, phase gate, as I think of it. In this case, we're implementing it near the center of mass mode frequency. So we have these states get pushed around the phase space, pick up the phase here, and this is the very standard gate which has been implemented many times around the place. I guess one point is that we could, because we have two different isotopes of calcium, we could work with calcium-40 and calcium-43. Both of them will feel this force. In principle, we could use this as an entangling gate to entangle a mixed pair of two different ions in a sense there. But at the moment, we've just been concentrating on working on this with calcium-43. We've also used calcium-40 because of the simpler level structure for various diagnostic stuff. Okay, and we generally do this double loop gate here, so that the gates are phase gates, so we wrap it in a Ram's experimental spin echo sequence to protect against spin decoherence. Here we're in field-dependent states in calcium-43. And we generally use this double loop gate as that corrects for unequal illumination of the two ions, even though it's a bit slower and gives us, therefore, more photon scattering. Here's a summary of various two-ion gates, which have been done over the years on optical and hyperfine clock qubits. So I think up here is about 3% is the original Boulder implementation of the gates from 2003. What else have we got here? We've got, this is Rowe's number he told us about the other day. These two are the Bermudez gate, which Andrew told us about from Boulder yesterday. One of these up here is from Chris Monroe's group as well. And this, of course, is the amazing result from Innsbruck, Jan Bellon's result from 2008 now. And don't get excited, I'm not about to show you data down in this region, but I've just taken the graph down. I've started it off here at that error correction estimate I showed you right at the beginning of 7 × 10 to minus 4, just to emphasize that there's still an order of magnitude to go here before we get down there. The diamond shapes are optical qubits. So Rowe's gate and the Innsbruck gate are on optical transitions, and so it's that one. These ones are the hyperfine gates over here. So that's what we're comparing with. So I want to look at the various different error contributions now. So what we've decided to do is to work at a constant Raman beam intensity. It's about 5 milliwatts per beam in a 60 micron spot. And then we can work out the scattering rate. So what we actually do to vary the gate time is to vary the Raman detuning. So up here is about 100 gigahertz, over here is about 1,000 gigahertz detuning. It's of course Rowe Azeri and others wrote the Bible on this photon scattering error some time ago. But we're not really in the regime where we need to discriminate between the Radial and Raman scattering, but the model has it all in there. And then what other errors have we got? Okay, so the other thing that as you try and go faster with your gates, if you're tuned near the center of mass mode, when the gate goes faster, the gate detuning has to increase, you get closer to the stretch mode, so as the off-resonant excitation comes in over here, so that comes in quadratically as you try and go faster. This over here, now slower is usually better, but of course eventually you run into heating rate or motional dephasing from the ion trap, so this is our estimate of where this would come in here. Now this pink line here is a very, very annoying error. This is the spin echo error just from doing the spin echo sequence that the gate is wrapped in. And the reason we have such a big error there is that we have a magnetic field gradient along the axis of the trap. So this is a 4-ion crystal. We're just measuring the qubit frequency for each different ion. You can see they're all come in, a few kilohertz between them. This is the crystal spaced a bit larger than we normally work with here. We have a gradient on trap axis of 0.5 milligauss per micron. This is huge. So Christoph Wunderlich told us about his lovely scheme for using the magnetic field gradient for addressing and so on. This is bigger than some of the gradients he gets when they're trying to have a gradient. So I think we must have made like the end cap out of samarium cobalt in this trap or something. So this is a bit embarrassing. Anyway, that leads to both an error in this time regime down here, which is just for the fact that your spin echo carrier pulses are not quite resonant with both ions. And it gets worse over here when your spin echo time gets longer, because there's also, imagine when you're in the superposition state in the free position of the Ram's experiment, the two qubits are processing slightly differently, so you get these bigger errors over here. So
all those lines are for the field-dependent qubit, is that
this right? Is all for the field-dependent qubit. Yeah, everything I'm talking about in the two qubit gates is the stretch state calcium-43. Okay, right, so enough with the simulations. We'll actually see when we go to the lab. So we look at the gate dynamics first. So Rowe showed us a nice example of that with 5 gates. We've only done 4 here. We're scanning the gate pulse times inside the spin echo sequence. keeping everything else constant, and measuring the populations at the end of the ions up, down, down, and the population of one ion, either ion. So we're not using camera detection, so we're just using 0, 1, or 2 ions fluorescing. This is what we see. So this is 4 gate periods along here, and this is a long run to get the shot noise down. So there's something like 3 hours worth of data here. And what is nice about this is that it's not a very high fidelity gate particularly, because there's a systematic missetting here. So the black and the blue curve should come together at this time and at this time. But apart from that, the data really does follow very closely this analytic model. So the line is an analytic model with no decoherence or anything modelled put in there. It's just what you should get if the motion is doing what it's supposed to. So it really seems like the motional control is following what it should be doing. By the time we've done about 4 gates, you can see there's a slight discrepancy from the curve there coming in at a couple of percent level. So what's happened here is that we haven't got the laser power quite right. So we haven't tuned up the laser power, so we're not quite getting the right phase in the gate. If we do tune it up correctly, here's the gate dynamics for a single gate. And you can see these lines then meet up more nicely. Okay, so now Chris Balance is really the guy who's doing this almost single-handedly, and he's done a fantastic job. He's been working hard in the lab and has taken a bunch of results now, and these are all his different experiments. So mostly what we're doing there is working, as I say, at constant power, varying the Raman detuning, and seeing whether we really fit our noise model reasonably well. And there's a couple of outliers up here, but mostly everything here is fitting with a factor of 2. So at the fast end here, we get 90% with a 3.5 microseconds. So that one is a single loop gate. These green points are sort of non-standard settings. Everything else is the standard settings with 2 loops. And over here, we get down to about 99.5% with a 100 microsecond time. So that's the best effort number. So I have one confession to make here, which is that this photon scattering error here, which we thought we understood, came out slightly wrong. And so we did another experiment to check this. So we looked at the gate fidelity. Instead of keeping the Raman lasers at constant power, we kept the Rabi frequency at constant power and changed the Raman detuning, and varied the Raman detuning of power, so we kept the Rabi frequency constant. And this way, everything stays exactly the same in the gate sequence and the gate detuning and so on. What we see here is that we do the scattering theory carefully, and we're working on our matrix elements carefully, and figure out what we're supposed to get. We get this green curve down here. If we carefully multiply that by number 4, we get a reasonable match to the data. So in fact, it's now number 2, so we've already found one factor. So we don't think it's anything interesting. We think this is just something boring. Because it matches the 1 over delta dependence so well, I think it's very unlikely to be... we think the experimental measurements are right, and it's just some boring factor of 2 somewhere. So we have to, of course, get to the bottom of that. So these are the other errors we've thought about. So we've effectively measured this scattering error and verified that. The spin echo error we can measure and calculate pretty easily. Other things we've estimated, which are all basically off the bottom of this plot here. Motional dephasing, well, that comes over here. Off resonant error, it's this one. Thermal occupation of the other mode, and so on. So things we know we have, but we can't model very well, are the laser intensity noise and that qubit spin decoherence. Okay, so I will finish there, summarize with the results. So the single qubit operations and 2 qubit operations here. We're obviously pretty pleased with those numbers. I guess it's been mostly a talk about technical issues, which is maybe not so surprising, given that what we're trying to do is make things better. And I would just like to thank everyone who's worked so hard to get these great results. So particularly Tom Harty worked very hard on the single qubit results here, and Chris Balance has just done an outstanding job on the 2 qubit gates, and he's really been doing that single-handedly, the modelling and the experiments and everything. And it would be very remiss of me not to acknowledge the enormous contributions of David Alcock, who got both this trap designed and made while he's with us, and started off another project here, which I haven't had time to talk about. Thank you very much.
Okay, thanks a lot for these nice results. David.
Nice result, David. Just to be clear, is it the belt state your fidelity? Or?
Yes.
Yeah.
Yeah. Yeah.
Further question?
So as a poor ignorant theorist, can you enlighten me to the footprint of all of the microwave electronics and lasers?
The footprint? You mean what?
Well,
like the technical overhead? You mean?
I mean, well, for example, you contended that microwaves are much more mature for this type of control. So, like, how big is your microwave control apparatus?
Well, it's bigger than it needs to be. I mean, okay, the microwave control apparatus that does the single qubit drive is a DDS board, which is about this big. So, I mean, there's a bunch of other stuff on the way to the track.
And it's essentially commercial off the shelf.
Yes, I don't think, David, remind me, I don't think there's anything particularly special about the microwave.
I think you could get the whole thing onto a PCB about that big if you wanted. Just
Yeah,
a few
it's
analog
not.
devices, chips.
So the microwave control then at this sort of subpart per million level
Yeah, I think so. I think
is largely, the art is not the source, but just getting it hooked up, right?
I think the art is getting into the trap efficiently, actually. So, I mean, I think it's where David is nice trap design is the thing that makes a difference there. But I mean, very similar results came from NIST when they did randomized benchmarking of a microwave-driven gate, and so I think the microwave stuff is pretty well understood there.
Yeah, but maybe one should say that all laser control is also microwave control, because the lasers are controlled through AOM. So, in fact, the part until it goes through an AOM is the same whether you use microwave control of the ion or the.
Yeah, sure, but the laser, I mean, you have to have that AOM, you have bulk optics.
I mean, well, forgetting even about the size, I mean, it seems like the power fluctuations in the microwave signals are much less of a challenge than the power fluctuations in the laser counter.
Yeah, I mean, that's why we would like to maybe go to a diode laser system to avoid these fast laser fluctuations. But then we're pretty sure that the laser intensity is not actually limiting the gate fidelity at the moment. So, the gate pulse is sufficiently long that those fluctuations average out quite well.
Okay, maybe just one very brief question. I mean, about your spin echo error. So this, I mean, specific to doing one pulse, so this would be reduced if you do two pulses or so. I mean, this is.
We looked at trying to do some sort of composite pulse sequence, like the corpse pulse sequence from NR people use to, where you can correct for the addressing error. But then it turns out you've become very, very sensitive to things like the pulse area fluctuations and so on. So we didn't think we would win by doing that. So.
Okay, and let's thank David again.